Okay, welcome everyone to the Harishchandra lecture series, and I'm very happy to announce our speaker for the Muruga Kingdom, who is from IT culture, and he's going to speak on harmonic analysis of complexification. Sorry for the delay.
Is it okay? Is it audible? Yeah. Thank you so much. And I really regret for this delay and happened. I'm reminded of a story, maybe you saw the story. When TV was invented, the authorities asked Charlie Chaplin to come and give a lecture. And he was only just moving his mouth, but he was not talking. And the whole team was struggling to find out what was the reason. The sound was not coming. But indeed, Charlie Chaplin was playing. So I thought I should also play with you. He's a mathematician. I shouldn't. This actually, I'm very grateful to the organizers, especially because there is some sort of a nationality. IISER is India. And I don't think many of us, many of the mathematicians know that there was a somebody by the name Harishchandra. Indeed, when I was talking with many people, they would be thinking about mythological characters that Harishchandra. So in that respect, I'm very, very happy. That's one of the reasons I came all the way to share my discussion matters with you all. And I am here to give 3 lectures on compact Lie groups. But perhaps I will not be talking about compact Lie groups. Mostly we will be talking about UN. See, this is a series of lectures. So far, I don't know how many of you have attended. There circle. So the group structure was put under the concept. So convolution, yes, there is a group structure, and there is something called character yes. But when you go at more difficult or general groups, even how do you view a character? And what do you expect when you want to have a character? That itself is a big question mark. So I first thought that I will give a little prologue about Harishchandra, or in other words, let us all sing the glory of Harishchandra for 2 or 3 slides, and then I will be talking generally what is spiritual theory today. Spiritual theory was done by my colleague Anna last week or 2 weeks ago. Maybe you would have forgotten. So I thought I should start with that, and perhaps I may not be touching upon what I am supposed to do today, namely the irreducible representation of the. We will do it so now in the next lecture. So now my time starts. Thank you. Okay. So this is Harishchandra, and I like it. There is no surname. You see that? I like it. And so this is what I call the dialogue. The main contributions of Harishchandra was to understand the non-compact semi-simple redo. So it is non-compact. Compactness is always good, topologically fine. You can manage. It is non-compact and semi-simple. Roughly, it is a product of simple group. You all know when there is a simple group, you may not have a normal subgroup. So when you want to understand a bigger group, you always look for a smaller group. That doesn't work here. And that's why it's very difficult. And we have done representation theory, which was discussed in the last lecture by Mona, but I will also recall them. In particular, something called discrete theory. And it was perhaps the first breakthrough in studying the representation These groups he characterized these figures based on the medical. And the characters, this is not something new for you, it is already said here. You looked at the characters sort of structure, similarly you looked at the characters on the real line, and then plan through formula. A lot of things were already taught, lot of things. There was a good amount of discussion on plan through formula on real life. But this is going to be this is indeed the magnum opus of Harishchandra. He finally given a formula for non-complex residues, which is actually indeed a great work, which is an outcome of monumental mathematical contribution to Harishchandra. I will not, so this is what Harishchandra has done, and besides that, lot of other things. So the mainstay for him is the representation theory of non-compact chemical groups. And I quickly go through fast. You already know what is a topology group, just topology is the group, and the relations should be compatible. I want them to be continuous. And of course, we say that the group is compact, so we use the topology compact, connected locally compact, and the language is compact. But for now, this is something you already know. These are the argument groups, and this is a non-compact argument. Also, see, actually, I fixed the notation for the discussion to come later. And there are locally compact argument groups. This is compact. This is the unit structure. But I am writing in this, I am writing like a quotient of two groups. So compact groups, this is the one which we wanted to look at, the UN, the set of all matrices whose inverse is the transport. And you have a smaller group of UN, namely the determinant one, and you have whatever has here it is FFC and here and here MNR or MSON. There are many other compact groups, but I will not be dealing with them. I think more. So these are the compact groups. The non-compact groups, this is a standard notation, GLNC, and similarly you have GLNR or certainly group, and determinant one, and NC. And just for the sake of completeness, I also include the Heisenberg group, which is almost looking like R3, but in the first two components we have addition, and in the last one there is a cube, and there is some simplex form coming up here, and that makes the group be non-abusive, but it is a good group, topologically beautiful thing, because it is homeomorphic to R3, which is indeed simply connected for those who know about. And now we slowly develop the tools to understand the groups. I want it to be locally compact groups, and I want a measure which is actually a replica of Dirichlet's measure. What are the properties of the Dirichlet's measure? Mainly, it has to be finite and a compact set, and for the open subset, I want it to be positive, and this is the most important thing. It is a left-finger measure, and that I write it in the form of an integer. Though in this lecture today I'm not going to use them, I want them to be, I just want you to know that the left invariant of a measure is actually the invariant of the integer length. And one may ask, why I assume it to be locally compact? The theory tells me that if I want to have a luxury of such a beautiful measure, I need the group to be locally compact. That is, I want the group to be topology. I want this to be a topology group, I want a measure satisfying the property, then automatically it becomes a locally compact group. If I am not wrong, it was proved by Mackey, and it was proved in 1930s. It is one of the very important tools for understanding the harmonic analysis. So I quickly give some examples. These examples are, this is already, this is Divyang measure. One important thing is there is a uniqueness which measures the property which I enumerated in the last slide, uniquely fixed. It has to be this measure are a positive multiple of this. So therefore, there is some sort of a uniqueness involved. The moment if you assume the group to be locally compact, and for this, this is the one you see that this appears in the Laplace transform. Those who study technology or engineering will know better, and this is the X. And in the Heisenberg group, the usual thing is a Haar. But I am not giving other examples. And when B is non-abelian group, one has to compute. What do I mean by this simple looking word, less sentence? I don't have to use the algorithm of size to really say that there is a measure energy. Here I use, if the group is compact Lie group, then I have the remaining matrix, and there is I have a Lie algebra, and through that the exponential map, I can really show you there is a. So this is the next one. This is going to be the mainstay for our next for this. Representation is actually, when I say that something is a group, the most important thing is the product. And that product I want to give in terms of the composition of bounded objects. So that is what roughly a representation means. I have a Hilbert space. I don't go beyond Hilbert space, and I want this is a unitary operator, and this forms a group. I want a group form also, meaning thereby whenever I have a group here in G, I represent it through linear operator. And it has to, and I also have to utilize the fact that G is not only group, it is a topology, it has a topology. I want this to be continuous. And there is a trick because U has many topologies. Bounded operators has almost 9 topologies, but I take this topology, this is strong operator topology. So example is trivial representation. So you have given a definition. The main thing is to look for the examples. The examples have to come from within, from the group. I have a group, and I cannot take any Hilbert space and I keep on talking about the representation. The group has to act. And trivially, every element goes identity operator is one type. It may look innocent, but it plays a very, very dominant role in the study of what they call groups with the property P. So then I have, because I have a Haar measure, I can talk of this Hilbert space, which you all know, R square integrable concept. And just now I told, while I was looking at the integral, the group conveniently acts on the bounded operators. By taking, I take a function F, I look at the left translate of F. So in some sense, you see that I am trying to understand this Hilbert space by allowing G to act upon LPG. There are two things happening here. One, I have the group, I have a representation, which is given through Harmonic. Secondly, wherever I have a space, I look at the function space. Here I have the group G. I look at the function space consisting of all firing the functions on the group G. I allow G to act and try to understand. So there are two things happening. Okay, I will explain this. I will come back to this little later. And this is called observer. So these are the two representations which God has given, and all other representations we have to construct. But when I said, if you want to construct, you cannot do it from, if it doesn't come from the heaven, you have to look for, perhaps sometimes I have to replace this by some other group, subgroup, or you look at instead of L to G, you look at L to G types, homogeneous space. Sometimes, like GL and C, act over CN, finite dimension vector. For example, look at UN. The easiest representation one can think of is the group of unitary operators operates over CN itself. So these are available, naturally available representations. And besides that, one has to construct. There is one way of constructing a representation called matrix masonry. We will not discuss it. Maybe later when somebody comes to talk about Harichandra's real work, they will discuss about English representations. And similarly, you have what's called analytic continuation of representation. These are all much more complicated. Fortunately, we do not have much problem. So whenever you have something, you look for irreducible representation. Like I always say, you look for prime numbers because you can write any number as a product of that. Similarly, I will understand a representation provided if I am able to write this as a sum of irreducible representation. The moment if I know irreducible representation, I will be knowing all the representations. So therefore, the main important task for us is to understand irreducible. The name itself tells you what you mean by irreducible. The only closed subspace which is invariant under G is the either trivial, only trivial, either 0 or the whole space. Sometimes all the irreducible representations turn out to be finite dimensional, which you have seen in the last lecture. Dr. Munana has proved that if the group is compact, then all irreducible representations are finite. And another thing is, we should not, so there may be two copies of the same which you will be looking at, which is meaningless. I say that these two are same if the operations are same and the Hilbert structure is same, meaning thereby there should be a unitary operator which transports this action into this action by means of C. For example, phi Tx can be given as C composite phi 1 composite E inverse C star. So therefore, I have to avoid it. So now this is what we call G denotes the class of all irreducible representations, which people call the dual of G. Sometimes it's also called it's the unitary dual, and G2 also has a topology, which we will not discuss. This one is actually beautiful, or it has more sectors when the group is RGB. We will come to that later. So the question is, in a harmonic analysis, at least representation theory of harmonic analysis, the problem is very simple to take to characterize Divyang. And that means that parameter. We will be parameterizing G hat tomorrow for 82, this for 3, and the day after tomorrow, in the third lecture, I will be talking about UN. So I write L2 harmonic analysis. What do I mean by that? I want to decompose the left regular representation, which I have given, into irreducible one. That is simply the meaning of L2 harmonic analysis I want to decompose lambda G into irreducible one. Have we already done like this? In which way it is useful? We will see. Right? For example, if you take a abelian case, this is Truth's lemma, which Mona the other day pointed out. This is Raychow's theorem. You say that a representation is irreducible if it commutes with every weight, then it has to be scalar operator. That is an operator representation is irreducible if the only operators which commute with the action are scalar operators. This you call it as Nash theorem in the study of finite groups, and this is true for every logical complexity for every representation. But there is a whole amount of mathematics is done to prove this. You read special theorem and some Caesar algebra business. Those who study functional analysis, they call it as Raychow's theorem, and those who study only group theory, they call Martin's theorem. So we will not worry about it. So therefore, if it is abelian, then all representation phi x will commute with phi x, isn't it? Because x and y commute. So therefore, it's a scalar multiple, and the only unit scalar is of the modulus 1. That is to say that every irreducible representation is of the form G equal to T R S. This is what you have seen 2 or 3 days ago. This is where you started your course of scheme of lectures. It is also forming a law. This is what I said. Structurally, it is very beautiful. Only it also forms a local compatibility group. And there is in 1940s, this theorem was very, very famous. And we put in duality theorem. What happens is I have a G, I got a G hat, which consists of all irreducible representations, namely characters. And it also formed a local compatibility. But then I would like to know what is double hat. And Pontryagin and duality theorem says that the double hat has to be equal to double. So this is so therefore, because of this, the doing Fourier analysis of G through G hat is successful. I simply push it under the carpet, saying that G hat is successful. What do I mean by that? And all that I will not start it. You would have seen to us for many lectures. You have Planck's theorem, and you study the functions through Fourier transform. If Fourier transform has some property, you talk about here, vice versa. And if the function is square integrable, Fourier transform is also square integrable. The guys in electrical engineering know better than us. So I will not do much about it. We will stop here and let's look at Fourier series. You already know the dual group is associated with integer. So these things I thought I should do it because there is a coherence of what you are studying. They are not separate components. You had analysis on real life. You had analysis on circuit. But the most important thing which is underlying is the group structure available in both. And you are writing like this. So what happens is you are taking a function f and you are writing this. You don't have to know harmonic analysis to know about this. You study it in function also. This means that the characters form an orthonormal basis. Right? So this is none other than Parseval's formula and some harmonic analysis of Planck's formula. Where you have, this is the inner product of F and the characters namely IISER. So, is it okay? This is what you study when you take G to be compact abelian. And today we would be seeing the same is true when I take a non-compact, compact non-additive. Is it okay? So I am writing, this is, maybe the name harmonic came because of this. You see that, yes, I am analyzing, I am writing it as a superimposition of, this is called superimposition by physics, and linear sum of harmonic, harmonic. So now when I have F, I have F pattern, analyze. And when I synthesize back, when I sum it up, I get back my F, the reverse process. That's called harmonic synthesis. And this one not only is done over forest, over heat, it's done on a general local comparative input in 60 steps. One of the main contributions in analysis. A lot of stuff. Okay. So this means I'm writing like this. You please try to understand the symbol. I'm writing the lambda left regular representation. You see that I'm taking L2 as direct sum of chi n. Chi n gives me one-dimensional representation. So I'm writing lambda as direct sum of one-dimensional representation. That is, lambda is completely reduced by means of irreducible representation. So therefore, the theory appears to be or otherwise. This is how I interpret the this is whatever we were discussing for the last 14 minutes is successful when I take G to be. Okay. So now, if you take Fourier transform on the other hand, it is not compact. You have G hat is given by again characters, but this time they are not periodic. I take I to be sorry, 1 second. I take sorry. Well, I'm not looking at only periodic function. I'm taking all our periodic functions on R. That's what the Planck function. You take any function, you write the terms of E for I by T. These are the characters. I'm writing F in terms of character. But now here what happens is it is not a sum, it is an integral. So therefore, here also I'm disintegrating lambda. I am parameterizing in terms of chi. You see that I'm taking lambda and it is given as a direct, not product, but direct integral of chi. So now when you go for non-compact thing, you cannot avoid direct integral. So when one ventures upon learning Harishchandra, one has to be ready to understand this.
What is the lambda?
Lambda is the left regular.
Okay.
The same thing. So here lambda is written as direct sum of chi n's, whereas here lambda is given as direct integrals of chi characters. So now, for the sake of, if you want to be a little bit cheap, if chi is not one-dimensional, here I will be having a representation. That means it is not a function. It's going to be an operator. Isn't it? For example, this is going to be an operator. This fellow, do you see that? So therefore, when I write L to G here, I'm writing the as a chain of one-dimensional representation. Whereas if I'm not lucky, then this one-dimensional representation has to be replaced by Hilbert space. Sometimes if you're lucky, you can do away with the final dimensional representation. Sometimes. Okay. So up to this, one can say that it is a warm-up. In order to understand what we want to talk, this is compact group. So we are looking at this drawing theory. it is one of the successful story in mathematics. Whatever we discussed for a C was done for a general compact group. I treated on the while. Maybe I could tell the story, Whale everybody knows. Why? So you will know. Peter did not do anything else later. He was a school teacher. He thought that he will use the theory, and he got into depression, and he did not do any mathematics later. But the whole world deliberates this theory. So this one I will not be proving. It is already done by Mona. Every irreducible representation is finite dimension. And if phi belongs to bigger, because it's finite dimensional, I do not discuss the degree also dimension, or it's called degree. D phi always denotes the dimension of the irreducible representation, which is actually finite dimensional. And so now, for every xi, I take a general representation. At the moment, if I plug in zeta, xi and eta, and if I move over function A, it becomes a function on G. So for a given representation, I always have a function, matrix Python. Do you know why do we call it as matrix Python? Because in a matrix, you know that the entries are given in terms of the entries are called Pij, that's given by Pj, comma, Yeah. So I call it as a matrix. And this one, study of this one was quite useful in understanding the representation. For example, this function, if I take a one-dimensional representation of R, which is a character which will never be square integrable because it's of modulus 1, and the measure which I look to is Liebeck measure is an infrared measure. So many times the important question one asks is, will it be square integrable? And the discrete series corresponds to that. I will come to it later. So the representative function plays a very crucial role in understanding representation. And please keep it in mind. Here also we will see that. This is easy to see because the topology given on phi helps you to understand that it's continuous. Because phi x is unitary, it is also bound. Now I denote all the representation functions. So all finite dimensional continuous. So I don't look at any general representation. I look at only finite dimensional because all my irreducible representations are already inside. Because irreducible representation always finite dimensional. This RG is sitting inside this set of our continuous functions. It has many beautiful properties. Let us see what that is. So now, if I have two representations are unitarily equivalent, then these two are same. So therefore, the matrix coefficient of another equivalent representation will not give me any new information. If two representations are unitary equivalent, these two functions are same. These are the functions on the group. And this is already done. And you take two irreducible representations, and you take two elements here, and you look at the product. This is a continuous and bounded function, so square integrable. This is also continuous function, bounded function, square integrable. So it will have a value. The value is 1 by n. You see that if they are equivalent, then it turns out to be it need not be 0. But if they are not equivalent, it is 0. So I take matrix coefficient of one representation, I take a matrix coefficient of another representation. If they are not unitarily equivalent, then the product is 0, L2 product is 0. Whereas if they are equivalent, that's given by constant, this 1 by n, I should have written as d pi 1, because if they are equivalent, naturally the dimensions are same, that is the dimension of the unit. It's called the Schur's theorem. Naturally, Schur was an algebraist, and this theorem was initially proved for finite groups. The physics call it as big Schur's theorem. So for them, there are two Schur's theorems. Let's see what is the other. Is it okay? And I will not prove it. This is done. This is where he stopped. Last time, the space of all representative functions form a dense space in CG. What is CG? We set of all continuous functions. And we know the Haar measure is topologically very well equipped, so that the losing theorem is valid. What is losing theorem? The continuous functions is dense in LTG. C not equal to infinity, it is dense in Rn. In particular, if I extend my first research a little further, I see that this is dense in LTG. So what is Rg? Rg consisting of all matrix coefficients corresponding to finite dimensional representation. And also you remember, whenever I have a unitary representation, I have one extra advantage. Namely, if something is subset, some subspace is invariant, its orthogonal complement will also be invariant, because U star is none other than U inverse. Namely, phi of x star is none other than phi of x inverse. So therefore, if you take any finite dimensional representation like you do on finite groups, you can write it as a direct sum of irreducible representation. So therefore, what is available here is Rg is actually linear sum of matrix coefficients corresponding to irreducible. So it forms a thing. So now I began with some irreducible representation, abstract irreducible representation. Through matrix coefficients, I am looking at them inside LTC. This is a trick. So, and also it underlines the importance of looking at the matrix coefficients. Is it okay? So this forms a dense space. Now, I don't know, do you learn the finite groups here? See, when you look at, it's not, you please learn it, there is a theory. If you have a finite group, you look at all irreducible representations over C, and if you want to be a little more advanced, you go for any algebraically closed or non-algebraically closed field. One, it is characterized by conjugacy class. If you look at abelian group, what is the number of conjugacy class? Equal to the number of elements. So you will have a lot of irreducible. If you have only one conjugacy class, then you will be having only one representation. So therefore, conjugacy classes parameterizes irreducible representation of finite group. Same thing happens here. I talk in terms of the class function. What is that? So I say that something is a class function. This name borrowed from algebra. Some analysts call it as a central function because it is invariant under inner automata. Okay. So now I did not explain earlier. For any function f, which is meaningfully good function, whenever this integral exists, for example, if f is continuous, yes, if f is L1, yes, because this is bounded, and so on. I take matrix and I apply that of it. So that gives an operator phi f on each element xi and eta. Phi of xi is uniquely fixed when I fix it for every eta, that's happens here. So I get a new operator. What is the use of this operator? I have an operator phi f, which is defined on the Hilbert space. Let's take, instead of taking just any function, I take a class function on L1. And then I look at this function phi f. What happens to that? This commutes with all operators phi g belongs. Because you look at phi x dot, I take an element x dot, then I throw it here, it goes as x naught here. And then I use the right invariance of the integral. So that x I replace it by x naught x, this x naught goes off. So this comes here because the Haar integral is what one calls right invariant. So now this one is by definition phi x xi eta f of x naught inverse. Now I use the fact that f is a class function, so that I twist it. I swap it. I got f of x naught inverse. Then if I redo the same thing, I get. So therefore, you see that in a non-trivial way, I use the fact that f is a class function to conclude that phi f is commuting with all operators phi g, where g belongs to f. What is the usefulness of it? I apply Schur's lemma and see that phi f is actually a scalar operator. If phi is a irreducible operator. But what is the use of having phi f like this? You will know in a moment. So therefore, every irreducible finite representation and so phi is realized inside the left field. So this one I have to explain. I take an irreducible representation. This was done by. I take a irreducible representation phi, and what happens is for every xi gamma eta, you have seen that phi xi eta belongs to L2 of C. So now that if I fix, for example, xi and eta, then I have a mapping which takes place to phi xi eta. It is from this to L2. And it was, I thought it was with us, but if not, I will explain more. This is actually, I am taking this fellow height inside L2. When I say that I'm taking this inside L2, what do I mean by that? Yeah, I have a, this should be a unitary operator. And then it intertwines with the action of G from left to right. Here I have the action given by phi. And here I have the action given by lambda, left branch. So the left branch, so there are two things I have to do. The moment if I put theta here, I look at the image, I have to see that that is invariant under left branch. That we actually use it, you see that here. I did, you see that I have x naught here, left translation. I throw it inside. So one thing I have to see that this is invariant under lambda. Secondly, phi intertwines with lambda. That is to say that I am realizing this representation inside the regular. See, I am giving you vaguely. Remember it, maybe tomorrow I will take just 2 minutes. So this is very important one. I don't know how I got it. I thought it was done. Is it okay? So, I try to understand. So this is important. See, I said that you have an abstract irreducible representation. I want to realize it inside the left regular representation. I realize it by this or by this point. But I should explain how it is being realized. I think. Okay. So now this is the other question. Maybe all right, I accept that everybody sits inside L2G, but I would like to know whether L2G is just this, nothing more. That is, I have left like Fourier coefficient on a circle. You take any function L2G that is given as the sum of harmonic e power IL. Similarly, I want any element in L2G as a sum of elements coming from L. So, what is the meaning of it? Can I break lambda into invariant orthogonal projection? So, whenever I have a subspace here in any L2G, for that matter, any single space, if I have a closed subspace, it is equivalent to having a orthogonal projection. That's what consonant is. Whenever I have a closed subspace, then I have an orthogonal projection. When I want it to be invariant, I want an orthogonal projection which commutes with astronaut. That means having a subspace here is the same as having an orthogonal projection which is not invariant. And if I want everything separate, direct sum, that means they should be mutually orthogonal. Two subspaces will be mutually orthogonal if only if P1 is perpendicular to P2. So therefore, I now change the language. Instead of looking at the subspaces, I am looking at the projection. I want to operate. Okay. So this is the answer. We do it through characters. So let me repeat once again. I want lambda to be direct sum of irreducible representation. That is the same as saying that I realize all irreducible representation inside left regular representation, number one. Secondly, I want to prove that these are the only way to do that. These are the only way you can do with a very square integrable function. That means I have to give orthogonal projections, and that is done through characters. What's the character? We go quickly. So this is for those who know. Actually, this came from algebra. In fact, historically, characters came first in harmonic, then came representation, even for non-obvious. Okay. So if this is the usual thing, you see that it is a sum of, it's only trace of an operator. So you can write it, and if these two are equivalent, the character is the same. And this is phi G of phi J, comma. This is the orthonormal. Phi J is the orthonormal basis, and it is continuous. Therefore, sum is continuous. and also the conjugate is also there. That's also character you get it through dual. This dual representation was also discussed by Bhimani. When he wants to use cone-wise theorem, he was proving that the representative functions form is flows as a complex conjugation because every representation will have a dual.
There's no sound.
So let's go back. I want a projection. That was the reason for me to introduce all these things. But instead, I have a character, a function satisfying some property.
Sir, you need to share the screen once more, I think. I am not able to see your screen. Your screen is not visible.
Oh, I see.
Yeah, I think only you have to share the screen. Yeah. And for some time, actually, you are saying something, and nothing we could not hear anything actually.
Yeah. Am I audible now?
Yes, sir, yes. Can you go back to the previous page? Previous slide.
This slide is not working. So
Yeah, this page.
What I wanted to say is, our task is now clear. I want projections, orthogonal projections on L2G to kind of give a product direct sum. I get it through character. That's what I said. And so it has this all the properties which you want. Actually, in fact, compact group has everything whatever you want in the study of representation theory. Is such a beautiful exhaustive concept. Okay, so then I have convolution. I define a projection here, omega rho psi x. Look at it carefully. If phi and rho are any two irreducible representations, I define chi phi. Chi phi is given in terms of rays of phi x. Now I look at this function. This function is almost like characters, except that there is a bar here for some reason. And also I don't like, see, you pretend that this is a projection. Then I want chi pi star chi pi to be chi pi. This is unnecessarily 1 by 2 pi d pi count. So I want to throw it, I put here. So now I the rho pi I take rho and pi to represent it, right? And I have chi phi. It's a function. Now, instead I look at omega phi. Oh, okay, omega rho. Omega rho, and look at this part. If I put a pi here, there is a magic taking place. This is a function. If I put a pi here, it becomes an operator. Do you remember? Pi f is by definition for any two elements is going to be integral f of x pi x I eta. Isn't it? Dx. So now this is an operator. This is an operator. Where does it act? It acts on the space x pi where pi is the reference. So now this satisfies it's an orthogonal filter space concept. Rho pi I am writing. Rho pi is an orthogonal position on the data. This is general theory. I looked at two representations, pi and rho, and pi I assume to be irreducible. And then I look at rho pi. Rho pi is given through characters, which is actually an operator on H rho. How beautiful it is! It is actually the orthogonal pi.
So pi is pi omega t.
No. This is actually pi of.
Okay.
Pi is irreducible. Rho is any representation. So therefore, for example, the very simple question, assume that rho pi is 0. When rho pi is 0, then the H rho, that is the representation space on which rho pi acts, does not contain pi. So that is an indicator whether the copy of pi appears in H rho. So, for example, when will the orthogonal position be 0? If the range space is 0. Similarly, rho pi will be 0 if H pi doesn't appear in H rho. So therefore, for example, you say that every irreducible representation is appearing in lambda. That means lambda of chi pi is not 0. It goes to the range given by the matrix coefficient. So this is what I have written. If two are distinct, then it has to be 0. So this is what you call again a fruit theorem. This is the Peter's fruit. You look at all matrix coefficients, it forms a dense. It's an orthogonal basis. See, psi I is an orthogonal basis for H pi. Psi j is an orthogonal basis for H pi. And using psi I and psi j, I construct a matrix coefficient. I put this fellow for some reason, root d phi. Then this becomes an orthonormal set in L2G. And the theorem says that L2, if I vary phi in G hat, I get all orthonormal bases. For example, go back to your Fourier series, G hat is integer. And because it's one-dimensional, it is going to be d phi is 1. So what is appearing here again. So now I told that when I was discussing Fourier, I said that what do we imagine for a non-abelian group? This is what one imagines. When it is non-abelian, there will be representations which are not one-dimensional. So therefore, it will have a finite orthonormal basis. Everything should be taken into account. So now, this is what Pedro says. You are writing L2G as a direct sum of V phi. V phi is actually n copies of H phi. You see that I fixed it up. I looked at it. Now I look at the orthonormal basis. If it is n dimensional, for eta 1, I will have 1 copy. Eta 2, I will have 1 copy. Similarly, I will have d phi copies inside L2. And it doesn't appear in your Fourier series because there it's one-dimensional. So therefore, d phi is off. You see that here also you can view that G hat is a discrete set. And there is a measure coming out. What I give is I give weight for each phi, I give the weight d phi. So therefore, the G, when I take compact group, G hat is a discrete. So now, generally, when I say discrete, all the matrix coefficients of the compact groups are found in the L2. Whereas when you go for non-compact, as I said already, you can't expect. But Harishchandra proved that it has the characterized when a matrix coefficient will be inside L2G. That's a fantastic result. It's something to do with the conjugate class of torus and so on. So this is now if my group is non-abelian, I look for class functions. I know that class functions every such I have I think I have to go faster. If you take L2G, this result I need it tomorrow. You write it as a beautiful orthonormal basis like this, provided S is a class function. The only difference is there. Okay, I think you remember. I will not explain. However, this forms an orthonormal. You know that chi pi is a class function. This is another aspect of Petro's theorem, which says that if I look at all class functions, this forms an orthonormal basis. How much time more I can take? I exhausted 5 minutes. It's okay. See, sometimes when there's a technical snag, I have to lose my mind. So therefore, it forms an orthonormal basis. So this you please remember. I haven't given the proof. This I will be using it. How do I use? You take a general compact group. I want to understand. I look at characters through by trial and error, some irreducible representation, I get it. Or God gives me like it gave to Ramanujan. And then I have to prove that these are the only characters. These are the only irreducible representations. That I can prove it if I prove that chi-phi is a complete orthonormal basis, because there is no other basis orthonormal element will come into it. So if I want to prove my bag which contains some irreducible representation is odd, I need to use this theorem. Tomorrow we will use this. I have given a proof. I think I don't have. So this is one thing. See, when you, how many of you have heard of the word Lie group? Don't worry about it. See, one important thing is if you take Rn, there is a, you look at some neighborhood, it will never allow a group inside. You take R, what are the subgroups you can think of? You have integers, rationals, and so on. What are the closed subgroups you can think of? Which are like integers, which they call solenoid. So, but if I take R, for example, I take -1 to 1 interval, what are the subgroups we can think of which is inside -1, 1 interval? The only subgroup is trivial subgroup, isn't it? So such a thing is called small subgroups which are non-trivial. So this theorem is important. Any compact without small subgroup is isomorphic to a subgroup of UN. I have given the proof, so therefore UN is important. There is a story behind this one. I will not tell you now. We do not have time. This is just a warm up for tomorrow's lecture, and also I did it today. So this theorem tells you that whenever you have a topological group, a locally compact group, which has one open subset which doesn't allow you to have a subgroup, if it is compact, then it has to be sitting inside UN. So therefore, UN has all the information of the general compact Lie group. A group is roughly topologically Lie group. A locally compact group is roughly topological Lie group if it has an open subset which doesn't allow a subgroup. Think that way, but we will come to it later. So this exponential map you already know, and the important thing is these identities. You don't worry. The only thing is this exponential is C∞ function. Is a C∞ function from MNR to an open subset GLNR, and it is directional derivative at 0. You know this notation, directional derivative at x in the direction of 0 is identity. So then inverse function theorem works. It says that by inverse function theorem, this exponential will be locally inverted. It's an isomorphism. So therefore, this you also have an inverse which is logarithm, which I will be using tomorrow. And this theorem tells you that GLNR, there is an open subset over which exponent is a dichromatism. This is what inverse function theorem tells you. And this doesn't allow smaller subgroups. That is a proof here. So now what I do is I look at all subgroups of GLNR which are linear Lie groups. These are called linear. Don't worry about the word Lie. I say that something is good if it is a closed subgroup of GLNR. What is the advantage of it? So far, I was looking at a topological groups. I look at it because I get exponential map for free. There is an exponential map, isn't it? Because it's a subgroup of GLNR, I have an exponential map. That exponential map will do not good, we will not say them. So this, maybe I will begin tomorrow. Now you are all tired. I am also tired. I will stop here. I have to define here. Right? Yeah, you missed one. In some quotation. What I'm saying is, whatever I thought is Ramayana, but we talk Ramayana many times because this work is done long ago. So it's a beautiful work, and I will be using some of the ideas which I discussed today to understand SU2, SO3, and UN in the days to come. Thank you. I will be sitting in the room number 415.
Also, one thing you told something about Max when you were telling about Haar measure. You told something about Max's result about the converse. What's that?
What the Haar measure is left in way. Okay, that's algebra. It's also topologically significant. It is regular in the sense that any measure of any subset, I can get it through below by means of the measure on compact. Or I can come from the above by means of open subset. Assume that our group, our sphere topology is second compact. All right. So now the question is, can I extend existence of a Haar measure for the topological groups which are not locally compact? For example, I assume that the group is completely regular, so that you have continuous one. Any locally compact space is completely regular. But the answer is no, because if you have a topological group satisfying these properties, then it has to be homeomorphic to a locally compact group, isomorphic. So therefore, I cannot go beyond locally compact group. The proof, if you want to read, I read from a book. Have you all heard of Care Farstadt? Maybe you cannot know. Care Farstadt, he wrote a beautiful book, Measure Theory. The last chapter contains. So the natural question is, what happens? Can I go beyond locally compact group? But of course, when you have a locally compact group, there are abundance of compacts which are important. That's why you study locally. But the answer is you can't go.
For existence of a Haar measure, locally compact group is necessary, right? That's what you said.
Yeah, right. Regular meaning that regularity. Yes.
Sir, actually, I just want to say, where you define this representative function RG. Can you just? So there actually you missed this. That should be span of matrix coefficient. There is only just not set will not be subspace, right?
No. RJ is represented matrix coefficient all finite dimensional representation.
A span, don't you need a span? Span of, because that may not be subspace, right? Only matrix coefficient of finite dimension. You are just taking the collection of.
Yeah, you take collection of all finite dimensional representations.
And then span it. Linear span.
You don't have to span it. You take
No.
F1. F1 is given by phi 1, xi 1, eta 1, phi 2, xi 2, eta 2. Take the direct sum.
Yeah. Phi 1, yeah, direct sum. Yes. Probably you don't need it. I think.
Right. And
lambda. Okay. Yeah, probably you don't need it. I sense.
That is one of the tricks I use when I want to prove, then actually I have to use spectral theorem of compact operation. If I take every irreducible representation, every sub-representation of lambda will have one finite dimensional sub-representation inside. To prove that, I need a spectral theorem. There is a different approach. So that's why I very carefully I took only finite dimension, not all. Or you took span of irreducible representation. Correct.
Yeah.
Okay.
Okay.
Any other question? No? Then let's-
I forgot to mention, please do come. Sometimes it's quite boring if I have to lecture only to the board. How do you fix it?
Okay, good.